is that, hopefully that's a little better on the sound, is that right? Can you hear me?
Yes, that is.
Okay. Yeah, for some reason my speaker wasn't coming up.
Okay, we are now live on YouTube. I am going to share the link with our attendees.
Okay.
Yes. Right, great. Link has been shared. We'll probably wait a couple minutes before starting. Shristi, you take it away. I will be here muted if you need anything. Okay.
Now, is it okay if I start sharing my screen, or is that going to work out?
Yeah,
okay?
yeah. Feel free to do that now or when you begin speaking. It's up to you.
Yeah, you have to enable the screen sharing. I'm getting a host disabled.
It should be good now.
Okay. There we go.
We'll give it a couple of minutes and we can start at like 2:32 or something, or 2:30.
Okay. Perfect. Yep.
All right, I think we're ready to begin. So hi everyone, welcome to our guest series events. Today we have Bill Mannel, General Manager and VP at HPE. And he's going to be talking about high performance computing. I'm really excited all of you are here. For those of you on our YouTube link, go ahead and share any questions or anything you might have during the talk, and we'll be sure to relay it. And yeah, I'll hand it over to Bill now.
All right, well, thank you, and welcome everyone. Thanks for spending the afternoon with me. I'm going to talk about a topic called high performance computing, and I'm not sure if any of you are aware of this, but it's actually a pretty interesting topic. It's been growing quite a bit. At one point in time, high performance computing was generally things that people at universities and governments did to solve some particular problems. But now we're seeing more and more that lots of industries are doing it. I'll talk about some of the applications for high performance computing in a moment. But it's becoming very popular. It's one of the fastest growing, we call it a workload in the computer industry right now. And so that's always a good thing. So, lots of people investing, lots of jobs, lots of new innovation, these sorts of things are happening in high performance computing. Now, in reality, it's been around for quite a bit, probably about 30 or 40 years or so, and I'll explain what's specific around high performance computing, but as soon as some of the technology was available, then we started to see it popping up. And again, typically it started with the government to begin with, and then slowly moved into universities, and now probably every large company is doing some amount of it. So I'll talk a little bit about some of the common workloads that we see, and workload, I use the term workload a lot, and a workload is basically what application, what kind of data that a customer is working with. And I'll explain that a little bit more as we go through the slides. So first off, the energy field is fairly popular and big user of high performance computing these days, and this actually includes not only just the more traditional energy of oil and natural gas, but also some of the new energies as well. So all the different ways that we get energy can be can be touched in some way by high performance computing. Now, the first of these is seismic analysis, essentially in seismic analysis, you're doing compute. So in other words, it's a compute operation, but what you're really trying to find is areas where there might be oil or natural gas. And basically what typically happens is that there's a device of some sort that's actually sending sound waves into the earth, and it could be on land, it could be on the ocean, but you're sending sound waves in the earth, and then you have microphones set up, and you listen for the waves as they come back, and from that you gather lots and lots of data. For example, in the Gulf of Mexico, which is in close by the Texas coast here, there'd be these massive ships that go out and they just drag these microphones while they're pulsing the ground underneath with sound waves, just recording, understanding it. And when you do seismic analysis, again, you're looking at all that data and trying to figure out where there might be oil. And sometimes, it's not a perfect science. Sometimes you think oil is here and you put down you do an exploratory drill and you don't come up with anything. So it's not a perfect science, but again, a lot of the analysis is done in high performance computing, and depending upon the complexity of the environment where you're searching for the oil, it can be even more high performance computing. So in other words, you actually need more high performance computing in places like the Arctic, where you've got ice and cold and very stormy seas and things like that can kind of impact the data a bit. So you got to do more work to get the data you want. Reservoir simulation is another interesting thing. So in this case, you've actually, a reservoir is you found a source of either natural gas or oil, and you're trying to figure out the best way of, we call it exploiting it. So actually getting the gas, the oil out of it in the cheapest way, fastest way possible from that standpoint. And so this is another area where high performance computing is used to figure out exactly, you found a point where oil can be, and you want to kind of understand what that reservoir looks like. Is it a big round sphere? Is it more elongated and stretched out? And you can do some of that work with high performance computing as well, and then determine where you want to drill or where you want to pump from that standpoint. Now, the other thing, as I mentioned previously, energy here is not just carbon related energy, but also around wind and solar optimization. So for example, if you're creating a wind farm, that is, and you've probably seen some of these there in, you go to West Texas, you'll see some of these. If you go up north around Newfoundland, you'll see these big windmills that are actually generating electricity and power from that standpoint. But kind of knowing where to put the windmills and how many to have and how big they need to be, that's a high performance computing problem. It's a very complex problem, and something that is done by high performance computing. So again, in the energy field, very large user of high performance computing, whether you're more traditional carbon based energy or your newer wind and solar energy as well. Now, another place that's very heavily used in high performance computing is in manufacturing. And so when we talk about manufacturing, we're actually, I see that as designing product. So it could be your cell phone, your iPhone. It could be a car, it could be a plane, it could be a building. So whenever you're designing those things, there's a number of things you need to worry about in terms of that. We'll talk about that in a moment. When you're doing, and one of the places that high performance computing is used a lot is what's called crash simulation. And you've probably seen on TV where they have a car and there's some dummies in there, and it runs forward and smashes into like a building or a block or another car or whatever. And really, that's a very expensive process, as you can imagine. So once you've kind of done it, everything is destroyed essentially, and you've got to start from scratch again if you want to run your next test. And so they don't do that for all types of crashes, all kinds of speeds, and so forth and so on. What they do is they they do a few test runs, if you will, and they gather some data. And then with that data, they build what's called a simulation. And then they kind of understand with that simulation, if you sort of crash it into a building once and it looks like this at say 10 miles per hour, this is what they think it'll look like at 20 miles per hour, 30 miles per hour, 40 miles per hour. This is what it might look like in a side crash. This is what it might look like in a rear crash. And so after they've done a few real crashes like you see on TV, it becomes a high performance computing problem. They go and gather data and then they run a whole bunch of simulations. And a lot of times they get a lot of data out of the simulation. And then they use graphics, complicated computer graphics, to actually analyze and see what's happening. You know, how does this portion of the car body respond when it sort of hits sideways into this fire hydrant or whatever sort of thing. So again, high performance computing application need lots of compute to be able to do that. Material science. So this is material science is basically how we build materials to make up the things that we use. So the body of your car, for example, that's a very complex thing. They call it thin metals right now, and it's gotten more complicated because we wanted to make them as thin as possible, as light as possible, and at the same time very strong. You know, so a lot of research goes into that. There's another thing called composites, where you actually, instead of using metal for things, you use various different combinations of materials such as carbon fiber and these sorts of things. So some of the new airplanes today, the Boeing 787, for example, is made up of carbon fiber. There's really no metal in that. It's just carbon fibers that are spun very tightly and very strongly to make that plane. And in order to make sure that the plane doesn't fall apart or pieces of it come off or whatever, you have to do a lot of research in terms of those materials, understand how they work. So again, a high performance computing problem. Fluid dynamics is basically how fluids can be water, they can be air. So these are things that move over time. How do they impact an object, a car, a plane, a house, you know, a wind turbine, as in the energy example I talked about earlier. And we do something called computational fluid dynamics, where we use, again, compute to figure out how this particular object, maybe it's a car, how that's going to act in different in different environments. So faster wind from the side, wind from the top. How is that going to happen, and how's that going to work? And why is it important is because with most objects moving through the air, we create something called drag. So any of you out there that may be mechanical engineers or not probably know about drag. Drag slows things down. We have to work harder to drive against drag. You know, just drive into the wind sometime and you'll feel that drag. And that reduces fuel economy. It takes us longer to get from point A to point B if we're an aircraft, for example, flying. So it's important to kind of understand that. That's where you get estimates of fuel mileage and things like that off of some of that drag data. Okay, so again, these are high performance computing problems. Financial, big industry. This has really grown significantly over the last few years. And typically, there's a number of things that are done with high performance computing. One is risk analysis. And a lot of times we also call this portfolio analysis, or that's probably one of the more common terms you'll hear. And basically, what you try to do is, a portfolio might be a series of stocks, and maybe it's in a mutual fund, or maybe you have a very rich investor. You're a person who helps that person invest their stocks, and maybe it's 30 stocks. And you want to kind of understand how those stocks could change over time, and you introduce new conditions, say the Federal Reserve rate or the unemployment rate, into that analysis and see what could happen to that portfolio. And it's a very complex problem, and we'll talk about that a little bit more as well. Algorithmic trading is another one, and that's where instead of a person making decisions, you actually have a computer making decisions. And so this has created a number of different issues over the past few years or so, but it does a similar thing. It kind of looks at what's happening with the market and says, oh, I want to sell this stock at this time. doesn't call anybody, doesn't call you if you're the person who has the stock. It just says, boom, I'm going to sell this stock right now. That's called algorithmic trading. Again, kind of looking at where the market's going and deciding at a certain time, I want to sell this stock. Very, very popular. And sometimes it calls things like flash crashes, they call them a little bit, where all the algorithms suddenly decide we got to sell, and the market just crashes. And so they've had to do some things to stop that. Again, high performance computing problem. Fraud detection, so this is where, someone, and maybe some of you who might have a credit card out there, get a call. It's probably an automated call. You're not really talking to anyone, but it says, hey, look, we think there's fraud on your account. We just closed your account. Please call this number. And basically in the background, whenever you're making a transaction, typically most credit card companies have these algorithms, these programs that are going on, and they're looking to see if fraud is happening. And they might look at a whole bunch of different types of factors. Where have you spent your money before? We just saw you made a transaction in Texas, but now this is a transaction in Singapore. These kinds of things they look for, and they look for fraud. And it could be your credit card, it could be your bank account, it could be all kinds of things. And again, high performance computing problem, lots of data, want to get a quick result, because if you allow that fraud to happen for too long, then you've got a problem, right? That you have to fix. And so, what we've found over the last few years, and this is why high performance is getting popular, there's more and more data out there. So, when you're on your phone and you're looking around websites and buying things or playing games or looking at news sites, that data is being gathered, and people are doing research on it to understand kind of your buying behaviors. And another high performance computing, by the way, is that we have a customer that is actually looking and saying, oh, I'm gonna send him an ad for Levi's jeans, because I know that this time of day he buys clothes, and we think he likes Levi's jeans, so we're gonna send him an ad. That's another high performance computing problem, because once you got to get that answer quickly so that the person can say, oh yeah, I'll click on this ad and look at these jeans. Okay, so again, explosion of data. We're gathering more and more data than we ever had before. We've got all these devices, cell phones. We've got the thermostat in your house is, if you have a Nest, is a device right now gathering data. Your car is creating tremendous amounts of data. Where you're driving, how the engine's working, all that stuff is getting uploaded to Ford, Toyota, whatever, and they're looking at that stuff. So huge amounts of data. And then meanwhile, on the right-hand side, you've got technology in high performance computing, or supercomputing. Sometimes it's called supercomputing, by the way, is exploding. So we can analyze so much more data than we've ever been able to do before. And so these two things are kind of coming together: lots of data and lots of capability of analyzing the data and building in this thing in the center, which is new applications. Now, traditionally, high performance computing was really a lot about simulation. So again, trying to simulate, like I said before, trying to simulate what the real world is in a computer. So maybe you're trying to understand how this car is going to run, how it's going to crash, how this plane is going to fly. Simulation, you're building a simulation to kind of understand what's a natural phenomenon. Another thing is cognitive simulation, and this is where a little bit like the fraud example, where you're gathering data, you're analyzing it, and then you're trying to make make decisions, or help someone make a decision from that data. So that's cognitive simulation. Moving all the way to AI, which you probably heard about. Everybody's heard about artificial intelligence, right? These people are going to, these robots are going to take over our life, kind of thing. But that's another place where it's actually automated. So the algorithmic trading I talked about earlier is kind of an example of AI. It's gathering data, based upon some certain conditions. It said, sell that stock, kind of thing. Doesn't come back to you. The computer's made the decision on its own. That's an AI type of problem. So again, the quick message is why high performance computing is growing. You've got all this data out there. You've got, a lot of capability, and you've got all these new applications in the center here that can use high performance computing. So I'm going to give you a very basic tutorial on high performance computing, so just to help you understand what this is about. First off, and I'm not going to do math here, so it should be very simple. So high performance computing typically is around partial differential equations, and so all of you, if you're going to engineering and computer science, will probably eventually have to take a PDE course. I did. I was a mechanical engineer. I had two courses of this stuff, and generally it's a lot of complex math. There's a lot of high precision there, and lots of data is used and generated or becomes an input or an output to that. So again, partial differential equations. That's typically what a lot of high performance computing is. AI, as I mentioned before, artificial intelligence is more about linear algebra. So it tends to be, don't get so hung up on low precision versus high precision, but that's kind of the accuracy of it. So high performance computing tends to be very accurate. AI tends to be less accurate from that standpoint, so and you can use less precise math, and so you could get more work done on the same kind of equipment versus high performance computing. So these are a couple different ways to look at data, basically. Let's just say that. The good thing about it is with high performance computing, other very smart people have done a lot of the work. so we know a lot of the equations that are already being used for this. And certainly if you go into engineering or computers, you're probably a lot of computer scientists here. You'll hear these equations depending upon the field you go into. So like in finance, there's algorithms called Black-Scholes. There's what's also called Monte Carlo simulations. These are all kinds of algorithms that are already available from that standpoint. Whether there's people write algorithms to simulate weather, hurricanes and weather patterns and rain showers and all this kind of stuff. Manufacturing, lots of people created algorithms around manufacturing. Typically computer-aided engineering is kind of the sum of that. And fluid dynamics, the Navier-Stokes are probably well known. I was a mechanical engineer, and we had to learn about these for fluid mechanics and heat transfer. So anything that moves, again, the fluids I mentioned earlier, is governed by Navier-Stokes equations. And then finally, for sales comp, this is an interesting one. Even for people who are doing that kind of analysis, how do I pay my sales reps? That's another example of some equations that people have built to make that happen. Now, probably the most distinguishing thing about high performance computing versus other kind of computing is that the problems are so big that you rarely use one computer to solve it. You could absolutely use one computer to solve it. For example, a computational fluid dynamics problem, a Black-Scholes problem, but it would take forever. You have a little processor made I'm in the laptop right now, a little HP laptop. I could run a high performance computing problem, and 10 years from now it'll finally be done, right? And so because these are such big problems, generally you want multiple computers to work together to solve the problem. Okay, let me repeat that. Multiple computers working together to solve the problem. And so these could be two computers kind of working together. Each kind of split up the job, and you take half, I take half, and let's work on it together and we'll get it done faster. There's actually computers out there where literally thousands of computers are working together to solve these massive problems. And keep in mind that, and you probably know this, that a lot of times a microprocessor within a server has multiple cores, which are kind of like multiple brains within that processor. So, literally there are applications that take 100,000 cores across thousands of different servers, and we put those together to create a supercomputer to do high performance computing. And again, this is because, some of these problems, it's useful to get them solved now versus 10 years from now by harnessing more computers at one time. So here's an example here where you've got basically a whole bunch of computers tied together around something that we call a fabric. Sometimes people call it the network. Some people call it the interconnect. So it's how the systems get connected together so they can communicate with each other. And sometimes they communicate and one computer gives data to another computer so that it can continue to do some other piece of work. Other times it's telling it, hey, look, I have a problem. Let me go, and you guys keep working. So sometimes that can happen. So a computer can fail in the middle of a long simulation, and it just shuts itself off and gives its problem to some other computer that just happens to be up and running or available. So again, to summarize, many computers working together, hooked together with an interconnect, typically is what high performance computing does. So this is just a simulated example of a computer here. So you have, let me see, you've got 8 by 8, so 64, sometimes we call them nodes together that are going to solve a problem. And so, typically these are great examples. This is a little bit lower level of data here. So you've got if you look on the left-hand side up at the top, you've got your 64 nodes together working on a problem, and they're actually bringing data in and out in something we call a file system. So that's where your data lives. And typically you're pulling data in, working on it, and then writing results back out. So that's typically a file system. Lustre is a flavor of file system, very popular file system for high performance computing. It's fast and can trade data back and forth and so forth. One key thing is if that input output happens slowly, it slows the whole problem down. So you want to have that happen pretty quickly. Then in the middle, you have an example of what's called the software stack. A lot of times you call it the runtime stack. It's actually pretty complicated. So this is how you run programs on that high performance computing machine. So typically you have what's called a scheduler, and the scheduler is basically something that decides who gets to run and where. So let's say, for example, you've got multiple users who want to use the same computer. It's a very big computer, by the way, at University of Texas. So let's say 10 different users want to use the computer. A scheduler comes in and says, okay, Joe, you get to use this part of the computer. Janet, you get to use that part of the computer. And Catherine, you can use this piece of the computer. And sometimes it can get more sophisticated and say, okay, Janet, you've got a really complicated job. You need these graphics processing units or GPUs for your job. You work that. And then, for example, maybe Henry comes along and he needs the same, but he's got to wait until Janet finishes her job before he can come on and use that part of the computer. In addition to that, there's compilers. We call them compilers and optimizers, and you're probably familiar with that. They take your source code, compile it into machine language, and as a part of that, they'll optimize it for the particular computer that they're running on. And then typically they use various applications and libraries to kind of pull all that together. And you can have a math library that does things like sines and cosines and all these kinds of things that can be pulled in at runtime to run those particular operations. Maybe it's a fast Fourier transform that you need to run, like in a seismic analysis. Remember I mentioned that earlier around oil and gas. They use a lot of fast Fourier transforms. So maybe you have a fast Fourier. There's a fast Fourier transform library that you can pull in and do Fourier transforms and help you in your analysis. And then finally, because a high performance computing system or a supercomputer is so big, you typically have a management stack to make sure all the parts are working and tracking errors and getting them fixed and putting a new operating system on, that kind of stuff. So these are typically key parts of a high performance computing system. I'm going to probably quit at that. And so we got a few more minutes. Any particular questions that I can help people with?
Yeah, so thank you so much. That was actually super, super interesting. We had one question from Aniza. She said, what aspects do HPC, AI, and deep learning technologies generally intersect on?
I'm sorry, which aspects? Is that the?
What aspects do?
What aspects? Okay. Yeah, typically, it's a really good question, actually. So today, it's a little interesting because, back 10, 20 years ago, you mostly did simulation. Okay, so you simulated how a hurricane was going to go from that standpoint. Now, more and more, because again, we have all this data, we can really combine high performance computing and AI together and get more accuracy, problem solved faster, these sorts of things. And the way that happens is that you're working on your simulation over here of how a hurricane would behave. And meanwhile, guess what? This was the worst year for hurricanes ever, right? So you had a lot of opportunity to gather a lot of data. And when you gathered all that data, you could then bring in analytics, which, a lot of you folks would call statistics. You probably took statistics in high school, or maybe you've taken it in college. You apply statistics to some of that data. And then you basically got two different ways of analyzing the problem. One is by simulating it, based upon kind of what you know about the various equations. Remember, I mentioned previously that these folks have built equations to kind of to simulate the real world. And then you've got real data. And then you can start comparing back and forth and saying, oh, okay, how is my simulation working relative to some of this real data analytics that I've done? Now, when you bring AI in, that's like really interesting, because now as your simulation is running, so you're actually having your simulation running, the computer itself can start doing comparisons and actually make adjustments. Sometimes, a long time ago, we called that computational steering, which means, as the simulation starts to go in a certain way, you take some of this real data and try to steer it in the way that it's more likely to come out. And in a way that happens within the machine. It's not, back when I, did this a long time ago, we looked at the results and said, oh, we need to change this. In this case, it can happen automatically, and all makes things faster, more accurate, and things like that. So it's very interesting question. But basically, most work today has some combination of both let's see, traditional simulation as well as new AI and data analytics that are applied together. And like I said before, it helps solve bigger problems faster and cheaper. So it's a great thing that we have that. Any other questions?
Yeah, and to wrap this up with one final question.
Sure.
What makes HPC and supercomputers different from quantum computing?
Oh, that's a great question. Okay, a lot of the things I'm talking about is pretty much traditional computing. Basically, it's more or less the way we've done computing forever. And at the end of the day, everything kind of boils down to a 1 or a 0. And basically that's not changeable in traditional computing. So you're either 1 or 0. The 1 or 0 can mean a variety of different things. Yes, no. You have data here, or you have no data. These sorts of things. And so that's a more traditional computing way of computing. Now in quantum computing, it's a bit different, and it's kind of hard to comprehend. But in quantum computing, at any one time, we call this a bit, and you probably heard that term. And that bit can actually be either 1 or 0. It's not necessarily at any one time defined to be one or the other. And so that actually allows you to solve problems in different ways. Before, you're kind of restricted. It can only be 1 or 0. And if it's not 1 or 0, then the problem doesn't solve. But in quantum computing, it can be either and both at the same time. So it's a little bit interesting. And that allows you to, again, solve some specific problems, hopefully very fast. There's not, it's very theoretical right now. I would say probably in like 10, 20, maybe 30 years, you could have a quantum computer on your desk. I mean, that's just kind of the nature of the technology. But again, follow that is very interesting, and a whole bunch of different ways they've done quantum computing over the years. I think that's probably, I think we're at the top of the hour. Yeah, we're a little bit over. So
We are, yes.
Yeah. So again, thanks for your time and attention today. And certainly, I'm on LinkedIn, by the way. If you have any other interest in high performance computing or supercomputing, happy to join your network. Anyway, have a great rest of your Saturday, and good luck in your careers and where you end up. Thank you.